Hello, today we're going to look at perpendicular and angle bisectors, two important geometry concepts here that both use a lot of perpendicular lines, have a lot of applications. Let's take a look first and see what we've got. First, I'll remind myself what it means to bisect. Bisect, of course, means to cut into two equal parts. As you notice here, you've got two pictures. This red line, the red line is bisecting the blue line. It is cutting it into two parts that are equal. Both of them are equal to a value of x. Same thing happens on this side. The red line is bisecting this blue angle. They're both equal to a value of a. So bisect means to cut into two equal parts. Let's first look at the angle bisector. It's any ray or line that cuts an angle into two congruent parts. And there's two fascinating facts about this that we're going to use. First, we recognize that the two angles at the bottom are congruent. That is the definition of the angle bisector, that is cut into two equal parts. So you have two congruent angles. Similarly, you also have that the distance from the sides of the angles, AB is a side and BC is a side, the distance from the sides of the angles to the bisector itself, which is always measured perpendicularly, will be congruent. So we end up with two facts here. One, we know the angle ABD at the bottom is congruent to CBD because the two angles are congruent. And we also recognize that ED and FD are congruent. So that's one thing about the angle bisector. Now let's see that in practice. First, give this a try on your own for a second. Wonderful. So we'll take a look now and see. We know that LMO and NMO here are congruent because they're marked with blue, and therefore we know that they're an angle, that OM is an angle bisector. Well, because OM is an angle bisector, I also know that OL must be congruent to ON. They must be the same because it's an equal distance from the two sides. Knowing that OL is equal to ON, I can substitute in with use my algebra skills, add 5 to both sides, divide by 4 and find out that x is equal to 7. Another one to practice. Try this one on your own. Excellent. So on this problem, I recognize at the top that LA and LB are congruent. They're marked as congruent and they're marked as perpendicular. So I know that they are, in fact, an equal distance from this line, which means that YL is an angle bisector. Therefore, I know the two angles at the bottom, AYL and BYL, are congruent, and I can substitute their values in. Using the distributive property here, I recognize that 7x plus 17 would have to equal 12x minus 3. I'm going to add the 3 to both sides and subtract the 7 at the same time, and end up actually, I did that backwards. I did subtract 12x, and then I subtracted 17. I ended up with negative 5x equals negative 20, and dividing gives us that x must be 4. Further, if I want to know the value of the angles, I can take that 4 and plug it in. Plugging in a 4 either into this x or this x, since they're equal, I find out that the size of the angle must be 45 degrees. We'll now look at our perpendicular bisector. Perpendicular bisector is any ray, line, or segment that bisects another segment at 90 degrees. In this situation, you can see that perpendicular bisector is CD. Here's the 90 degrees, and here is where these two are equal. Two interesting facts from the perpendicular bisector. One, we know that the segment is cut into two equal parts. So AD in red and BD in green at the bottom must be equal to each other. We also find out that any point on the perpendicular bisector must be an equal distance from the endpoints, AB. So in this case, C is on the perpendicular bisector. Therefore, we know that AC in purple must be the same distance as CB in blue, which tells us that CA is equal to CB. Let's see that in practice. Give perpendicular practice number 1 a try. Excellent. So you recognize that BC, by all of its markings, is clearly a perpendicular and bisector. So I know that AB must be equal to DB. Substituting those values in, I know 7x plus 10 equals 9x minus 2. Subtracting 7x from both sides, I get that 10 is equal to 2x minus 2. Adding 2, and then dividing by 2, I find out that x must be equal to 6. Another example. Try this one, perpendicular bisector practice 2. First off, I recognize that QO is a perpendicular bisector. Here's the perpendicular, and I'm just giving you that information to start with. Because I know it's a perpendicular bisector, because I told you it was a perpendicular bisector, we now know that MQ must be congruent to QP, which means that 11 is equal to 4x plus 3. Subtracting 3 and dividing by 4, we recognize that x is equal to 2. Now a teaser question was, L is on QO. Can anybody tell me why L is on QO? Well, of course, it's because L is also marked as being an equidistance from the endpoints M and P. Therefore, if I were to extend QO up, it would land through point L. Just recognize that in all of these situations, perpendicular lines keep coming up, and all these right angles lead us to many opportunities to use some more mathematics, including the Pythagorean theorem, right triangle trigonometry, lots of isosceles triangles, and many more concepts. Thanks for listening.